All right, so we're actually getting some calculations here of probabilities. So not much has changed here from the last time we were calculating probabilities. It's just trying to get the mean and standard deviation. So a probability distribution of means of samples of size n's tells us the probability of getting a particular sample mean among all samples of size n. So it's telling me the probability that I would get that mean across the board if I took every single sample that was possible, and I found that mean. So for a four-sided die, we took samples of size 3 and we got the probability distribution above. So we saw that one earlier. So if I simply just ask you what's the probability of getting a mean of 2, that's going to be 0.156 or about 15.6%. This means that the chance that if I had to remember, these are samples of size 3, this means that the chance that a sample of size 3 has a mean of 2 is 15.6. So we're not looking at this as individual values. When we're looking at these probabilities, we're looking at the probabilities of getting particular means. So that's really the hard part to try to wrap your head around, is that we're looking at probabilities of means, not X values. So I'm not saying what's the probability I roll a 2. I'm saying what's the probability I roll a die 3 times and the mean is a 2. Same thing here. This isn't the probability that my dice roll is 2 or less. This is the probability that I roll a dice 3 times and its mean is less than 2. Actually, I'm going to 2 or equal to. I need to make a quick little fix here. Or equal to. So if we did that, that's just these 4 numbers here. If we add those together, we're going to get 0.313. So this means the chance of having a sample size at 3 a sample size of 3 has a mean of at most 2 is 31.3%. Like I said, it's not individual values being less than or equal to 2. It's having means of samples of size 3 being less than or equal to 2. So just for practice, what we need to do here if we're asked these kind of questions. So recent data from the US Census indicates that the mean age of college students, so mu, is 25 years with a standard deviation of 9.5 years. A simple random sample of 125 students is drawn. What is the probability that the sample mean age, that's telling me I'm looking at an X bar, of students is greater than 26 years? So to assess this, I need to know the mean of my means, and I need to know the standard deviation of my means. I'm not looking at comparing this to the population. I'm comparing this to a population of means. My X bar is 26. And I need to compare this to a distribution of means because it is a mean. So I can't compare it to just mu and sigma. It means I need to have mu sub X bar, which I know is going to be the same as mu. So I know that mu sub X bar is going to be 25. I need sigma sub X bar, which I know is just my population mean divided by the square of the sample size. And we were told right here that we're taking a sample of 125 students, so that's my sample size. So sigma sub X bar is going to be the population mean of 9.5 divided by the square root of my sample size, so 125. Oh, I'm actually not going to round this. You can, if you do, you're going to get 0.85. Actually, let me double check this quick. Yeah. That's an approximation. So I'll show you what I do in the TI-84. But what you're seeing here is it's telling you that we're just trying to figure out what is the probability that, oops, sorry, my stuff's getting in the way. The probability that the mean age of students is greater than 26. So I'm looking at 26 or larger. And this is a population of X bars. All right, so let me go to the TI-84. Okay, so like I said, the important thing is that we realized that we're looking for an X bar. All right, so if I go to second bars, we're going to go to normal CDF. So remember, we're bounding this by the lowest number I can have, which is 26, and the largest I can have, which is 1. And we're going to put as many zeros after we can, because like I said, this just keeps on going on forever and ever and ever. So remember that the mean of my population is 25, and the standard deviation is 9.5, and I can put it right in here, divided by second x2 to get square root of 125. So I don't necessarily have to go back and figure out that it's approximately 0.85. I could just type this in here and get very exact answers, which is very close to what we had on the other slide. What we're getting here is a 0.1196. So the probability is about 11.96%. Lost my thing here. If you look on here, that's really, really close. We got 0.99797. That was because they used a rounded version of the standard deviation. I just used an exact version. Okay. I don't know what's doing there. I was catching on something as I'm trying to move. If we were asked this kind of question instead, the mean age of college students is 25 with a standard deviation of 9.5 years. A random sample of 125 students is drawn. We want to find the 30th percentile of the sample mean X bar. Once again, because we're asked for X bar, we know we need to have mu sub X bar, so the mean of the means, and we need to have sigma sub X bar, which is going to be 9.5 divided by the square root of 125, or approximately 0.85. So in this case, we have an area and we're trying to go backwards. So we're doing area and going back to find an X bar. So we do pretty much what we did before, was we use the in norm. So we have to put in, remember when we're talking about a 30th percentile, that means that we're going to look at 30% below. So whatever that percentile is, P30, what we expect is that this side of the distribution has an area of 0.3, or like I said, that 30%. So remember, when you're doing the in norm, we're doing area to the left, then we are going to have the mean. For this time, because we're talking about X bars, we're going to do the mean of your X bars, the mu sub X bar, and then we're going to have the sigma of the X bars. All right, so I'm going to take this to the TI-84. So we're going to go to second and vars, the distributions again, but this time we're going to number 3. And remember, we're just keeping everything area to the left. So the area to the left is 0.3. The mean of my distribution is 25, and the standard deviation is 9.5 divided by second X bar. So we get the square root of 125. So I get a very exact answer here. And I go to paste. And what I'm getting here is that this is, remember, because we're going backwards from an area. So we're doing area. Instead of an X, we're doing an X bar. So my area was 0.3, and we're getting an X bar of 24.5. So my 30th percentile is associated with an age of 24.5. So what we're saying here is 30% of college students have an age below 24.5 or 24.6, actually, if I rounded this correctly. So just one more problem with this. Then we're going to do this other set of problems and go a little more in depth. So here, cattle are one of the most popular, Hereford cattle is one of the more popular breeds of cattle. Based on data from Hereford Cattle Society, the mean weight of a 1-year-old Hereford bull, so their bulls are 135 pounds, and they have a standard deviation of 97 pounds. What would it be unusual? So we'll talk about that again. Would it be unusual for the mean weight of 100 head of cattle to be less than 1,100? So we're being asked mean weight of 100 cows. So we're taking, 100 cattle or 100 bulls. And what we're saying here is that we're looking at a mean weight is going to be 111. So we want to know, what is the probability the X bar is actually going to be less than 111? Because that's what we're asking right here. Would it be unusual for the mean weight of 100 cattle to be less than 111 pounds? So the only way we can assess that is look at probabilities. Okay. So we have a bull that is 111 pounds. We know that the mean weight we have a sample size of 100 bulls as well. So the mean weight of 100 bulls should be still 1,135 pounds. And the standard deviation in 100 bulls, as according to their weight, should be 97. And we're divided by the square root of the sample size, so we're going to divide by 100. Or this is going to be 97 over 100, or 9.7. So this one, because the square root of 100 is 10, we don't need to worry. We can just, like I said, get a whole number. We don't have to keep the square root in there. So we want the probability that the mean of these 100 bulls is going to be less than 1,100 pounds. So we're looking at a less than. I'm looking for this area to the left. So we do second bar, and we're doing number 2 because we're looking for, we are taking a value and going back to an area or a probability. The lowest limit, the smallest I can possibly have, we're gonna put a -1 and then a whole bunch of zeros after it because this keeps on going forever in this direction. I top out at 1,100. The mean is going to be 1,135, and my standard deviation is 9.7. Okay, so if you get this E here and it says -5, E is telling me that really what I have here is I'm going to have this 4, and the decimal place is going to move to this side, or anyways, I have this 4.7, 4.47. The decimal place is going to move this direction by 5 places. So 1, 2, 3, 4, 5. So we fill this all in with zeros. So the probability, if I clean this up, is going to be 0.1234447. So is this unusual? Well, we would say yes, because my probability, my P here, my probability that I would find that my 100 bull cattle have a mean weight of 111 or less. That is definitely less than 5%. Remember, 5% was that boundary where we started saying things were unusual, and this is well below that boundary. So actually, this is one of the things we frequently do with samples because samples have less variation. Or sorry, sample means have less variation in their values. They have small standard deviations. Do we usually use this to assess probabilities to decide if something's unusual? So I would say it is very unusual for a group of 100 bulls to have a mean weight of less than 1,100 pounds. The probability of this event is 0.0, oops, 0 point, keep missing, 0.000447, which is less than 0.05 or 5%. So anything has less than a 5% chance of occurring is when we start considering kind of unusual. So what this tells me is that I don't usually, I would expect a bull, just a bull would to weigh 111 pounds. Or sorry, 1,100 pounds. I would totally expect that to happen. That is well within the realm of possibility. What I don't expect to happen is that I collect 100 cattle and I find a mean weight, and that mean weight is at or below 1,100 pounds. That tells me that for some reason I have a lot of bulls that tend to be a little smaller than they should be. So they're a little underweight. So I have an abnormal amount of them that are underweight. That means there's something significantly wrong going on with these bulls that's causing them to be smaller. We expect one bull to weigh under 1,100 pounds. We don't expect mean weight of 100 bulls to be under 11,000 pounds. That means that my group of bulls have a tendency to be underweight. Now, there's something that's causing that to happen that I need to look into, but this is part of what we do when we look at sampling distributions, is we're trying to assess when something is really kind of like weird. Because when something is weird, that's when I really need to look at it. Would I expect to find my 100 bulls would have a mean weight that's under 1,100 pounds? I don't. That means I have to go back and try to figure out, well, what's going wrong that's causing my bulls to be underweight. Okay, so a couple more questions, kind of quickly go through, sort of look at difference here, but we're kind of trying to get a general idea of what we're doing. We're doing a sampling distribution. So we know the mean IQ scores of all adults is normally distributed with a mean of 100 and a standard deviation of 15. We use this quite a bit. So I looked this up the other day. The mean IQ of serial killers. So we took 4,743 serial killers, gave them IQ scores. So like I said, we usually use serial killers because serial killers is a group of people that we've actually assessed over and over and over again. So we have a lot of good IQ information about them. But we found, despite the common belief that they tend to be higher in IQ, that their average IQ is actually 94.5. What is the probability that a randomly selected adult has an IQ of 94.5 or less? So pay attention to what you're actually being asked here. What is the probability that a randomly selected adult? We are looking at an X. So because I'm looking at an X, that means that I just need to have mu and sigma because I'm just dealing with a population distribution. Like I said, we're just dealing with a population distribution. We didn't talk about anything about means or anything like that. We are just talking about it. So you just have to be a little careful and pay attention. Are you being asked to look at an X or are you being asked to look at a mean? So in this case, what I'm really looking at, this is red over here. I have a distribution. I want to know what is the probability that a randomly selected adult has an IQ of 94.5 or less. So we're looking at a less, so we know how to find this. And we're looking at a mean of 100 and a standard deviation of 15. Okay, so let's go look at the TI-84 and see what it has to say. I'll write that again one more time. That we're just looking at 94.5. And because we're just talking about X values, we're not talking about X bars or anything like that. It's just X. We just need mean. And we just need a standard deviation. And remember, what we're looking for is the probability that X, just a single person, has an IQ of 94.5 or less. So, second stat. So we have that negative whatever number. So like I said, we're going forever in this direction, and then it gets bound at the top by 94.5 because that's the IQ. The mean IQ of all people is 100, and the standard deviation is 15. So we have the probability here is 0.357. So we have a 35.7% chance that just anybody that someone's IQ is under 94.5. So totally likely. We expect like I said, this is about a third of the population. I expect about a third of my population to have an IQ of 94.5 or less. It's not weird at all. It's something we perfectly expect because 94.5 is still within that range that is considered a normal IQ. This is a perfectly normal person. Okay, so let's ask this question slightly different now. So the IQ score of all adults are normally distributed with a mean of 100 and a standard deviation of 15, once again. What is the probability that a random sample of 15 adults have a mean IQ of 94 or less? And then we don't know, is this unusual? Is this an unusual mean for a sample of 15 adults? So I'm giving you a sample size here, and then I ask for a mean. So what I'm looking for is an X bar. So I'm saying that my X bar is 94.5, which means I need to look at this as a sampling distribution. I need a sampling distribution of means. So I need to have my sigma sub X bar, and I need to have my, mu sub X bar and my sigma sub X bar. So remember, mean change, mean is still going to be 100. The standard deviation is different because the standard deviation is going to be that 15. But now, because that is what we normally have, and then my sample size is 15, so I'm dividing by the square root of 15. All right, so I'm going to take this to the TI-84. Okay, so over here is what we gathered before on just a single person. There's our problem, which is we're dealing with a sampling distribution. So we have X bars, and we're looking at 94.5 or less. And we're assessing what is the probability that a sample mean is less than 94.5. And I'm just going to add on here for a sample size of 15. So if n was 15. If n is 15, what we're going to get is that we're going to get a mean of 100 because well, that doesn't change, but my standard deviation for my sampling distribution is going to be the 15 that I had before, divided by the square root of my sample size, which happens to be 15. I'm going to do second enter. All right, so I can change it actually right in here, but let me go here. The distribution number 2, everything's the same except now my standard deviation is going to be divided by the square root of 15. Let me look at that again. All right, it's different earlier. Let me just check something. Okay, I don't know what happened the first time because I didn't really change anything, but I just did it again. This is what I should have had. The mean here is going to be this. Or it's not my mean, I'm sorry. My probability is going to be 0.078. We'll round out 3 places. So there is a 7.8% chance that a group, so when this is talking about an individual, this is probably the group of 15 people have a mean IQ of 94.5 or less. So these are 2 different questions. The first one, the one in red, like I said, that's just about an individual. I totally expect to find a person with an IQ of 94.5 or less. That represents a little over a third of my population. Because like I said, 94.5 is still within the realm of normal IQ. So I do expect to get some people that are going to be in my normal IQ range, that are going to fall under this category. And then, like I said, there's still a whole bunch of other people are going to be, maybe not in the range of what's normal, but they're still going to have an IQ over 94.5. I just totally expect that I randomly grab somebody and this is possible. Like I said, there's one or 3 people, if I randomly grab them, have an IQ of 94.5 or less. Now, if we talk about a group of people, you're going to have some people that 94.5 IQ. Should have some people, if it's a normal population that you would usually gather, you'd have some people in the 94, you'd have some people like 106, you'd have some people around 100, you might get 120 in there, but it probably balanced out by somebody that's like 170. You're going to balance out across that 15 people. Those 15 people should be averaging a 94.5, or it should be averaging closer to 100. So it is not as likely that 15 people altogether have an IQ close to 94.5. That would mean that you have a lot of people who are in this range here. So many people who have a 1/3 probability of happening are happening. Is really what we're saying. So there's too many people with this lower IQ than I would normally expect in this sample. So it's not as likely to happen. It's not improbable. It's not unusual because it's above 5%. So not unusual. Because the probability of occurring is over 5%. I still expect it. I don't expect it nearly as much as having one person have an IQ of 94.5 or less. But it's not completely unusual. So we're going to change this problem just one more time. So we know that the serial killers that we tested the IQ of, we had 4,793 of them. So what is the probability that if I did a random sample of 4,793 adults, not just serial killers, just adults, what's the probability that their mean IQ would be 94.5 or less? And is this unusual to get a sample of 4,743 adults and get this particular IQ? So compared it to our last problem, we're still doing pretty much the same thing with we need a sample mean, or we're looking at samples, so we need the mean and standard deviation for sample. So now we're looking at a sample size of 4,743. That means we still have a mean IQ of 100 for our samples. The standard deviation of samples of the size should be 15 divided by the square root of 4,743. We're still looking at the probability that somebody's IQ is under 94.5. So we're looking at the mean, or not somebody's, the mean. We have a group, just the size of a group, and their IQ is under 94.5. And once again, I'm going to put here for this particular sample size. So my standard deviation is much different now because this is going to be very, very small. If I plug this in my calculator, because I'm not changing too much, I've still got the same boundary, mean still same, except standard deviation I have to change. So now dividing by the square root of 4,743. And here I get 0. So when I'm not going to say 0, I'm going to say almost 0 because there's still a small chance. So there is almost no chance in a group of 4,743 average people, everyday people, having a mean IQ under 94.5. So you will sometimes get probabilities of 0. Just bear in mind that there always are, it's not exactly 0. It's very, very close to 0. There's almost no chance. Like there's a very small one, a very insignificant small chance, but a very small chance that this could happen. But the probability is almost 0 that if I took 4,743 everyday people and that I would find that they had a mean IQ of 94.5 or less. So with serial killers, this is what we're seeing in serial killers. We're seeing a mean IQ of 94.5 or less. What we're saying here is that we would not expect to see this out of normal people, which is telling us that serial killers are a very special subset of the population, which I think we knew already. But there's something important about their IQ. Their IQ is somehow connected probably with their being a serial killer because it's not probable that it would randomly gather people and they would have this IQ score or this mean IQ score. Like I said, we'd expect a person to have that IQ score. That is reasonable. I kind of expect, just barely would expect that if I had 15 people, that their average IQ is 94.5. But you have 4,743 people have a mean IQ of 94.5 or less is almost unheard of in your everyday people that you gather wandering through the world. So that the fact that serial killers have this mean IQ is, like I said, it's really telling that there's something very, very important there. So is this unusual? Yes, this is unusual. And this is what we're usually looking for when we're looking at groups, is we're looking for what is unusual. It's like if I went to assess serial killers, and what are the things I need to assess to understand them? If I look at their average age and their average age matches the rest of the population, then I wouldn't look at it. If I look at their IQ and their IQ looks like the rest of the population, I won't look at their IQ. But what this is telling me is their IQ is not like the rest of the population. It is special, it is weird, and it is unusual. I would not expect this to happen. Therefore, there is something important about that IQ and how it's connected to being a serial killer. All right. So one more problem for practice. I'm still trying to build up what we're doing here. So IQ score of all adults are normally distributed with a mean of 100 and standard deviation 15. If we have a sample of 4,743 adults, what is the first quartile for the sample mean? And then what is the third quartile for the sample mean? So remember what I'm looking here. Let's go back to the other screen. Is we're still looking at a sample size of 4,743. Mean still 100. Standard deviation is going to be that 15 divided by the square root of 4,743. And the two questions we're asked about the first quartile of mean IQs, and we're asked for this is actually D, and this was E. And we're asked about the third quartile. First assume this is normal. I don't have to look for the second quartile because I know that should be 100. So what we're looking at from our first question is, you remember quartiles splits the data in the bottom 25 and the upper 75. So wherever Q1 is, this area below it is 0.25. If we're talking about my third quartile, that's breaking up the bottom 75 from the top 25. So this area below it is going to be 75%. So we're talking about having an area and we're going backwards and finding an X bar. We're going to go second bars. And we're doing number 3, inverting the normal curve. The area to the left is 0.25. Your mean for IQs is 100. And the standard deviation is 15 divided by the square root, because we're doing a sample size of 4,743. And like I said, we're just doing to the left. For your first quartile, it should be 99.85. Really what it's saying is that if I have a group this big, that the mean IQ should not really be that far from 100. So this tells me that for serial killers, serial killers are well below into that first quartile. Now, if I do the third quartile, all I'm doing is I'm going to go back to the same thing. So number 3, but now that area is just 0.75. Nothing else has changed because we left everything else the same. So my third quartile is going to be 115 approximately. So that means if I had a distribution of my mean IQs, really it's just like 50% of samples of size 4,743 have a mean IQ between 99.95 and 115. That is what I'm learning here. So like I said, we can go backwards, but remember what it's telling me is it's telling me about means. So if I collect big groups of people like that, what I'm expecting is 50% of my population should be between 99.85 and 115. Once again, a little bit more proof that finding a group of 4,743 people with a mean IQ of 94.5 or less would be extremely rare.